So hi, everybody. You are welcome to my very first and hopefully not last live attempt at showing people how to code. So this may go a little poorly, may go pretty well. Let's be optimistic about it. In case you're wondering who I am, I'm Russell Spitzer. I work at Datastax. I'm one of the engineers on the analytics team, and that means I spend almost all of my time thinking about how to have Cassandra interact with all of the big data tools that are out there right now. Obviously, everyone's biggest interest at the moment is Spark, so our big focus is on the Spark Cassandra Connector, which is an open source piece of technology that you are welcome to check out at any time. And we are hopefully still going to continue working internet. Nope. There we are. So it's an open source project. You are welcome to check it out, help contribute, learn all about it, and all of that. But today I'd like to go over just a first application example. And to do that, we're going to start out by going to that link that I had on the meetup event. And that's Datastax Spark build examples. So if you've checked this out before, it's actually a pretty interesting repository because it has within it these two folders, Java and Scala, and inside of each of these folders are 3 subfolders, each one with a different build tool. So whichever build tool you like the best, we already have a pre-built, pre-set up build file for your application. And even better than that, if you go into the directory, we have one for Datastax Enterprise, which is our commercial offering, as well as one for open source software. So to start out today, I've just got my own little repo folder here, and the very first thing we're going to do is just clone this directory, clone this project into our own directory. So in case you've never done that before, basically what we're doing is taking the repository and all of its links from the website and bringing them down to our local system. Within that, we're going to then just pick out the build file, the build project that we're interested in, because we're not going to actually be using all of the various combinations at once. We're just going to use one. So let's just grab the SBT and open source example. And I'll go over exactly what's different between DSC and this. So basically, let's just grab this whole thing and copy it over to a new directory, call it example. All right. So we basically have everything we need to start working on this project. If we start up IntelliJ, which is my preferred editor, we can now import this. So we go to live demo and example. And the reason you want to do this instead of trying to import the entire package is that the full project has all of those different build examples, and your build system will probably just get confused about which one you're actually trying to use. So click on that Use Auto Import. Make sure you've got 1.8 set, and hit Finish. And you will begin the pretty short process of IntelliJ loading up everything in this SBT file and getting you set up with your own brand new little project. All right, so there we go. We got our nice little project here. And while it's busy indexing, because right now the very first thing that IntelliJ is going to do is run our SBT file and compile our code. While it's doing that, it's going to pull down all of the different resources. You can see down at the bottom there's this thing popping up with lots and lots of different dependencies. And basically, it's going through our build file and grabbing everything. So well, this is going to be a little different. Let's refresh that. There we go. OK, so this is the build file. And while we're indexing, I'll just kind of go over what this means, what do all these lines do. So right up at the top, we have some pretty self-explanatory things. We have the name of our project, what version we're using, what version of Scala we're using, and then 2 little personal variables that we're going to use here. This particular build example comes already set up with the connector 1.6.0 and Spark 1.2.6, or 1.6.2. And you'll see down here in our library dependencies, we have 4 different things, but they're all marked as provided. So provided in this context means that when we build this jar, if we happen to build a fat jar or what they, a jar that has all of the dependencies included within it, all of these lines will be excluded. The reason we want to do that is that when we're running our project, we do need to have Spark Core, Spark SQL, the connector, all need to be compiled against our code, but they're going to be provided on the class path by various Spark tools, so there's no reason for us to include it within our own jar. Now, all of this is actually going to be put together using the assembly plugin. So we have a little file here in project called assembly.sbt. You could also do a plugins file, but basically this just says that we're going to use the assembly tool, which will, if we uncommented any of these lines, would allow us to include other dependencies in with our application jar and have them included in a fat jar. So once this whole thing is ready, we should be able to go straight to our application, and everything should be highlighted correctly, and we have this beautiful little thing here. OK, so I'll go through this code in a second, but before we do that, let's talk about how we actually build this code. So the first thing you're going to want to do is go to your directory here. You now have these two IntelliJ metadata things. And we're going to call SBT assembly. So SBT assembly is going to call on that assembly plugin to build us the fat jar for our application, along with all of the dependencies that aren't provided. Currently, all of our dependencies are actually provided, so this is actually not going to merge anything. It'll just build our code and make a jar with it inside. And you'll see now we've got this nice little write assembly 01.jar. So some of you might have tried to just run this jar, and unfortunately Spark doesn't make it that easy. We can't just run our jars and expect our class paths to be set up correctly. Instead, we have to use something called Spark Submit. So to set up our little local testing environment, one of the first things we're going to do is download and install Cassandra and Spark. So I'm not going to do those myself right now, but the links are here, cassandraapache.org. We're not going to download 3.9. If you aren't aware of how TikTok works, 3.0.9 is currently the most stable branch. So if you're going to download Cassandra, I would suggest grabbing this, 3.0.9. And then for Spark, since we already have our build file set to Spark 1.6.2, we're just going to download that one. So we'll pretend that I downloaded those, and I basically just downloaded them and extracted them to my two favorite directories. One is Cassandra installs, which has all of these great versions of Cassandra, and I can just choose the one that we're going to run this time, which is going to be 3.0.9. And I'm going to just start it up. So to start up Cassandra on your laptop, right after downloading and extracting, you really don't have to do anything if we're just going to be testing things out, running our code, making sure everything hooks together correctly. So we just run bin Cassandra. It's going to spew a lot of text out at standard out. And when it's done, we will have Cassandra running on our machine. If you want to test that everything is working correctly, you can always just do bin cqlsh. And we can see, oh, everything's here. We'll select everything from system.peers. And we see we have no peers because my laptop is sitting all alone by itself on this podium. All right, so we have Cassandra running. The next thing we need to do is start up a little Spark cluster. In case you're wondering, we're not going to be doing the integration testing today because I decided that the way we currently have to do it is a little too complicated. I'm going to fix that in the next few days and probably do another talk on that later. But let's grab our Spark. I guess I have a slightly different version than I said. But once you do that, to start up your Spark cluster, just go to sbin, and then you can run start all. So to make sure that your Spark cluster started up correctly, what you're going to do is check the Spark master UI, which is going to be at your local host 8080. And you'll see now I've got a lovely Spark cluster started up. We're going to take note that there's a master URL right here. That's going to be a little important in a bit. But let's start out just trying to run our application now that we have both of these things running. So one thing that we're going to be using a lot is Spark Submit. So that is in the bin folder inside of your Spark distribution. And you'll see we have Spark. Oh, sorry, I have CD at the front there. Let's not have that. Bin, Spark, submit. Fun little tool. It's got a lot of different options, but basically what you need to know is that Spark submit will do a couple important things for you. The most important thing it's going to do is it's going to put Spark on your class path. It's going to put it on the class path of your driver application. It's going to put it on the class path of all of your executors that are starting up. The other important thing that it's going to do is it's going to actually distribute your application jar to all of your remote executors. So if you're not using Spark Submit and you notice that you end up having a lot of class path errors whenever you have remote code running, it's probably because Spark Submit was doing a lot of things behind the scene that you didn't quite notice. The other really cool thing about Spark Submit is that it reads the Spark defaults file. So you'll see that in this install, since we're just running out of a tar, we have a file in conf called Spark defaults. And this file will actually let you set a whole bunch of different options that will be set inside of your Spark configuration automatically when you run things. So this is basically a way around having to hard code different configurations into your Spark conf and instead just have them automatically kind of read out of the environment. You can also do them on the command line, which is what we're going to do now, that we're going to launch our little application. So let's go to our little live demo. We have our example. We had our file. I'm just going to quickly build it again just so I get that link to where it is. And I'm going to show you two quick ways of launching it. So the first time we're going to launch it, we're going to launch it using the local master. Now, local doesn't actually mean that it's looking for something on this machine. Local, when you use that in the master argument, actually means that what it's going to do is run everything inside of one particular JVM. So that means that there's no remote processes. Everything is happening within the same JVM in different threads. There's no issues with serialization. Nothing really gets moved anywhere. So it's really good for debugging. It's really good for setting up. But it also means that things that you see when you have the master set to local will not necessarily be the same as when you actually submit your application to a remote cluster. So we're going to do a Spark submit. We're going to set our Cassandra hosts, Spark Cassandra connection host, so that we don't have to have it hardwired into our code. And we are going to add the packages for the Spark Cassandra connector. So, sorry, that was me auto-completing that. But basically, the Spark packages right here, Datastax Spark Cassandra Connector 160S210, sets that runtime availability of the Spark Cassandra connector and all of its dependencies on the driver and on all of our executors. So if we were running this in a distributed environment, if we use the master set to the address on this web page instead of setting it to local, we would see correctly distribute everything. So when we run this without saying -- master, what actually is going to happen is we're going to run this all within the same JVM. So if I look over here on my, my master application, you'll see it doesn't even say anything's running, because we haven't actually communicated with the master. We're running everything within the application JVM. And you'll see it did some fun stuff. We can go over the code in that application a little bit, but you'll see we've successfully run. We read some data via the Spark context, and we wrote some via the Hive context, and it was very exciting. So that wasn't distributed, though, or at least it wasn't even in different JVMs. If we want to do it in different JVMs, we need to go back into our very long command line and add master and add a master address. So, well, I happen to have a master URL right here. Now, if you're using Mesos, this is the point at which you would use the Mesos address. But we're using just a tiny little standalone cluster. And now when we run this application, we will see that it shows up on our master UI. Very nice. This is going to do the exact same code, so it will be very less than exciting. But there we go. All right. So we've run our first bit of little distributed code. Let's take a look at what's actually happening here and how it works, and mess up a few things just to show how you can basically troubleshoot some things and work with the system. OK. The very first thing we're doing here in our Scala code is we're extending app. So for those of you familiar with Scala, this basically says that everything that happens within this definition is going to be treated as the main method. It's basically a shortcut of saying, I'm too lazy to make a main method, just realize that everything I'm about to write is main. This is pretty nice. Let's pretty quickly get into the meat of things. So the very first thing we're going to do is start a Spark conf. When you make a new Spark conf like this, it's going to inherit everything from your Spark defaults, from any command line arguments, from any environment variables. So basically, all of that is going to get fed in to this particular invocation. You're also free at any time to continue to set whatever you like. You can set spark.whatever to whatever you like, and that'll get carried through. But in most cases, anything that you think might change at some point in the future, you probably want to do on the command line or on the Spark defaults. A good example of this is your cluster management system. So say you're using Yarn, and tomorrow you want to run your application on a Mesos cluster. Well, it would be pretty unfortunate if you hardwired your master into your Spark conf, because that means you have to recompile your application just to run it against a different resource manager, and that's kind of annoying. So I like to keep that sort of stuff out of my Spark conf. The only thing you actually need to set is your application name. Everything else you can basically pass through on the Spark command line and have set correctly there. This next little bit of code is our first little bit of communicating with Cassandra. So starting with this Cassandra Connector conf, what this is going to do is use the Spark conf and look for any of the Spark Cassandra Connector connection variables. So you'll notice that when I started this, I used --conf. And from --conf, I used Spark Cassandra connection host. Well, if you go to the documentation here, we have a ton of stuff in connecting, but I'm going to go straight down to the reference file here. And in the reference, you can see we have a whole set of connection properties. So for example, the one that we just set, connection host, is the contact point, the initial contact point for a Cassandra cluster. So again, this is another thing that probably makes more sense to pass through on the command line than it does to actually set programmatically, because you might be changing your contact points, you might add additional IP addresses, you might do all sorts of different things. And the other big thing to note here, let's see here, is our most common issue with streaming applications is this parameter here, connection keep alive in milliseconds. So the code that we're looking at over here in Cassandra Connector conf, when it actually makes its connection to Cassandra, it's actually using a pooled cache of connections. It's going to compare the configuration that you've passed in against any existing connections, and if any do exist, it will return that rather than establishing a new connection to Cassandra. So this means that when I call this Cassandra Connector in conf code, I'm actually getting something out of a cache. I can actually call this inside of a map, inside of some kind of parallel operation, and continually get references to this Cassandra connector object, and it will always be the same session object. So I can actually use this thread safe, remote safe, doing all kinds of cool stuff, and not have to worry about it. But it's also good for this kind of mundane stuff, like just setting up a key space if it doesn't exist, and running code with it. So this little with session do basically says, give me that session out of the cache. I'm going to execute two little pieces of Cassandra code. If I was a little bit nicer, I'd probably check for errors here and handle them gracefully, but we don't have time for that. All right. Once we've done that, we move right into actually setting up our Spark application. These two lines here, the new Spark context and the new Hive context, this is basically how we talk to the resource manager for the very first time. So this Spark context line basically says we need to talk to the resource manager. We need to get a certain amount of resources. We need to set that all up, and I'll be waiting until that's ready. So if you take a look inside of a lot of the Spark configuration options, and I don't really want to go into all of them, basically what's going to happen is it's going to request a number of cores and a number of RAM, or an amount of RAM for the resource manager. And it's basically going to say, I need these things set up, start up these executor JVMs, which are separate JVMs, and have them contact me. And when I say me, I mean the driver application. It's really important to know this when you're working with Spark, that basically your application is managing all of the resources after it's reserved them from the resource manager. After that point, the resource manager is basically out of the picture. So at this point, we've gotten our set of executors. We've got this nice Hive context, which is how we can do SQL. This is a little bit different in Spark 2.0. At this point, it's, in Spark 2.0, it's basically a session object, but it's basically all the same code. All right, so we have that. And the very next thing we do is we do this little SC parallelize. Parallelize is our way of taking an array that exists somewhere on our local machine and moving it out to our distributed machines. So this parallelize 1 to 10 basically says I've got the numbers 1 through 10. I'd like them to be split up into pieces and placed on all of my executors remotely, so each of them has a little bit of that range to work on. And then our next little bit here merely maps that single number into the number, a tuple, a 2-element tuple, where the number is repeated twice. So that, as set, is actually good to save into our Cassandra. So basically, this will then trigger all of this work to be done, and a bunch of rows that are just 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, all to be saved into Cassandra. And you'll see our table here is really just KV, so that's why we map there. For more complicated mappings, I would check out our documentation. We have a lot of information on how you can map to more complicated row patterns using UDTs and things like that. Below here, I'm showing exactly how we can read that data right back out. So the save to Cassandra is how you take your data from an RDD, which is what this SC parallelize does. That it's a resilient distributed data set. And it takes that RDD and puts it into a Cassandra table. The Cassandra table call does the exact opposite. It takes a Cassandra table, pulls the data out of that, and gives it back to as an RDD. Our collect action here basically says the moment we've gotten that data out of Cassandra, it's going to be remotely pulled on all of our different executors, a little bit at a time. Bring it back as an array so I can take a look at it. This is almost always not the right thing to do, but in this demo, this is just an example of what you want to do. In almost all cases, you never want to collect your data after you've pulled it out of Cassandra unless you're absolutely done with it, unless it's the results that you actually want to do something with. Everything else should probably be treated on the server. So for example, let's say I wanted to take this data, and instead of doing this collect, let's read it in as a tuple of 2 ints. And this is allowed because one of the cool things the Spark Cassandra connector can do for you is it will automatically take the data that's in your table and map it to tuples, if that makes sense. And since we have a KV table of just int and an int, we can do that. So let's say we want to take that, and let's filter out all of the elements where they are the same. So we have this cool little bit of logic here. Actually, I'm going to just skip the Hive context because I know we're already running a little bit slowly, and I'd like to actually show how little of this works. So we've got this little piece of data here. We do this. We can then collect it, and let's just print that out. All right. So if we want to quickly run our code again, we have to rebuild it. And like I said, we actually don't have any extra dependencies here, so we don't actually have to use the assembly command. If we really wanted to, we could just use the package command, which will build the jar as well, and just use that. But since I've already got this command line already very long and written out, let's just quickly run it. And you'll see we're going to run this fun little piece of code. In case you aren't familiar, that little display that just kind of popped up is actually, oh, sorry, that was not as exciting because this is, let's just do that. that little progress bar is actually showing us how many tasks are left to do and how many have been completed. So in Spark, all of your work within an RDD is split into partitions. And as every partition is worked on, that work is called one task. And basically, a task will last from the beginning of reading a data into the point at which you have to shuffle it. Once you have to shuffle your data, you basically have to stop, collect all of your things together, perform this large shuffle operation, and then you come out of it with a new stage, which has its own set of tasks. So we do our little assembly here. Let's run our jar. I should probably switch back to local mode because it'll be a little bit faster than this, because every time we run this, we have to actually start up a whole nother set of JVMs after we start up our very first JVM to actually run our information. And we can see that our data is empty. Hooray! So we successfully did some distributed filtering on a trivial data set. It's not too exciting. But let's get into some of the gotchas here. Say I was really confused about why this was happening. I'm sure something that a lot of people would really start to do just right off the bat is they would take this code, and you know, if you're like me, I should say maybe not a lot of people, but this is what I would do, is I would just put a nice little print line right in the middle of my code, because I don't actually trust computers, so maybe it doesn't really know that X and Y are the same, but I know they are. So I'm going to just run that example again. And surprise, surprise, I'll spoil the lead here, nothing is going to get printed out. And that's really disappointing because I put a print line there, and that's like 99% of how I debug, is I put print lines places, then I like to see what prints out. Nothing printed out, very disappointing. So the reason for that is that when we look at our code here, inside of this filter operation, all of that is actually being distributed out to this other JVM, this executor JVM, which means this implicit system.out.println is the system.out of the executor JVM and not system.out of the application I actually just hit enter and ran. So how do we fix that? Well, the very first thing you can do is you can actually take a look at what your executors had in their standard out and their standard in. And I think the easiest way to do that is let's go right to where our Spark directory is. So this is going to be dependent on how you've set up Spark. But basically the same thing applies in almost all the cases. We will have a work directory. And obviously, I've been practicing something. And every application, every Spark context that you create is going to have one of these directories, this application directory. If you go inside of it, you will get this fun little, I'll show you this first. We get a 0, and that is the executor number. If I have multiple machines, each executor's JVM number is going to appear here. And then within that, I'm going to get all of the jars that got moved out. So this is, like I said, you didn't see me actually having to move all of these jars or save them at any point. But when I said -- packages, it basically says, make sure you get all those things that I said I actually needed in that dependency. So all of this stuff is getting brought in because of -- packages. But down here, we see these two great little things here, standard error and standard out. So let's take a look at what happened in standard out. That was not exciting. I think I have the wrong application ID, so I'm going to just wipe that out. See, live demos are a lot of fun. Let's just wipe out our work directory.
Did you recompile before you did compile it?
Oh, yeah, that would also do it. I'm a pro, guys. Don't worry about it. So we rerun our assembly, because sometimes we forget to do that. When we run it once more, we are not surprised that nothing prints out to our standard out here, because we're running with a remote master, which means that the code is actually being run in a different JVM, so we don't see printouts all over the place. Something else is very upset at us, but it shouldn't be a problem. And now let's take a look at our directory. And there we go. One of the cool things you should notice here is that we get things in pretty much random order. And the reason that we're getting things in pretty much random order is because Cassandra is returning them in pretty much random order. If you know how Cassandra works, our partition keys are not actually organized by their value, but organized by the hash of their value. So we're going to get stuff in a kind of strange order. And that's basically what I wanted to show you there. So you might be asking, well, I really want to debug in a faster way. I'm only using one machine. I want to quickly see my printouts, all of that stuff. Well, what we can do is remove this little hook onto our standalone Spark master, and it will default to local mode. Now, in local mode, not only is it going to start up a lot faster, because we don't actually have to wait for remote other JVMs to start, we're going to go right into everything in the same JVM, and the standard out is going to be correct. So you'll see now all that great stuff just printed out right there on my standard out. OK, so that's a little bit about how you can work with code, work with a Spark Cassandra connector, some very basics on how you set everything up and run tests. I would be remiss if I didn't do a quick overview of the difference between doing this and doing it on DSE. So you'll notice the big difference in the DSE build file is that there's only one dependency, and that's this. And that's com.datastax DSE, DSE Spark dependencies, and then whatever version of DSE you're using. That's going to just be a catch-all for all of the things that DSE is automatically going to put on your class path. So if you do DSE Spark submit, we actually will make sure that all of those jars will be on all of the executors and on the main machine. So basically, this is going to cut out having to actually call -- packages. Instead, you just call Spark submit, DSE Spark submit, and it will automatically do all that for you. The other cool things that it will do in shortening our command line significantly is it will actually make it unimportant for us to specify the Cassandra connection host. And because that's automatically going to be determined using the DSE machine that you're running on, although you can still set it to something else. And it's going to automatically set the Spark master to whatever the DSE standalone Spark master that's running is. So all that stuff will kind of get set automatically. So I think that's probably a good place to stop. This should be enough to just kind of get your own copy of this started up, start debugging things, and start figuring out why different pieces of code work the way they are. And I think we'd be fine to take just a few questions before we move on to the next speaker. Yeah? Sounds good. Yeah, in the back?
I'm a neophyte, so I'm not sure if this makes sense, but when I see those intermediate operators being chained together, it sort of reminds me of RX Scala, observables, asynchronous data streams. Or am I going down the wrong path?
Please repeat the question from the report.
Yeah, so the question is about, this looks a lot like a reactive kind of pathway where we're moving around elements, immutable elements, and we actually are. We have RDDs which are immutable, and we're moving them around. This particular piece of code works on RDDs, and if you look into Scala, or look into Spark, the reactive-ish equivalent is something called Spark streaming, which is something called D streams, which have the exact same API. But basically, everything within Spark is I have this large immutable object, this large immutable data set called an RDD, or a data frame, or a data set. There's a lot of different words. It gets a little confusing. But they're all basically the same thing. We have a huge set of some kind of element. Those elements are going to be treated with some set of operators. And at the end of the day, I'm going to do something with this set of operators. Now, they don't actually get treated in a streaming fashion unless you're using D streams. If you're using RDDs, they're going to be treated as basically a large block of data getting you can think of a large block of these things being moved onto an execution platform, iterated over completely, and then another block taken.
So that would be the synchronous case. The other is the asynchronous.
Yeah, so the way Spark streaming works is it's a micro-batching approach. So it's basically doing this in a mini version. So there's a lot of talk on the mailing list right now about moving towards a more purely event-based model, something like the way Apex or Flink works on things. But currently what it's going to do is take the data that's incoming, build these small distributed data sets, and basically treat those little chunks as a little iterator, operate on the whole thing, take the next one, operate on the whole thing, work on like that. So any other questions? Way down there.
How do you handle multiple tables? Because it like Cassandra is just picking up the one table in your session?
So save to Cassandra is picking up the arguments here. So the question is, how do you save to multiple tables? So save to Cassandra table is actually taking 2 arguments here. Let's have IntelliJ help us out here. There we go. First is key space name. Second is table name. So my key space is just called KS. My table name is called KV because I'm very boring. And then at this point, we have our column selector. So the column selector is actually where we can start doing mappings and saying like, well, the element you're about to read is going to be called foobar, but we actually want it to be bar foo. So do that mapping, and you do that within this selecting object. Any other questions? Yeah.
Is there a difference between the community version and the DSE for distributing to the Cassandra nodes, distributing the jobs to the Cassandra nodes for data locality?
So the question is there a difference between the community version of Cassandra and the Datastax Enterprise coupled version of Spark and Cassandra and locality? For locality, there's really no difference here. All those features would be the same as if you set up and configured your own cluster with Spark and Cassandra running on the same machines. The big gains you're going to get from DSE are a few of the things we have around cluster management. We have automatic failover of our Spark master, things like automatically telling you where the Cassandra connection points are and making sure that the application is always up to date with that. So a lot of maintenance tools and enhancements around there. But performance-wise, the two are basically equivalent at the moment. Yeah? What was the question?
The performance, you said it's a combination of Spark and Cassandra versus just Cassandra by itself. They both perform the same way.
I'm sorry, I don't understand.
You mentioned about both perform the same level of performance.
The community edition and the enterprise edition of Datastax. I mean, so the question is, what's the difference? What was I talking about with the difference of performance there? And that's between the community version of Cassandra and the Datastax enterprise version of Cassandra. Currently, the two are very, very similar. The things you got to think about when you're setting up your own Spark and Cassandra integration is, are you going to run Spark on the exact same machines that you're running Cassandra on, or aren't you? With DSE, it's basically going to automatically enable you to set up Cassandra and Spark with just a flag switch. If you're not using DSE, you basically have to make sure that all of your processes are co-located, make sure that they all are reporting the right IP addresses, because the way that Spark provides information about data locality is through the bound address of the executor. So you have to make sure that when you're binding your executor JVMs, when they're binding addresses, they need to bind the same addresses that Cassandra is going to report, because otherwise there's no way of the two being matched up, and you don't get any locality. Yeah, in the back?
So, like, is there any better initial setup? Let's say, like, you can use something like Maven project or like Gradle that can to get all this stuff out most without downloading and especially installing something.
Yeah, so like I showed at the beginning, the link we have here has a starting Spark build examples at Datastax. We have Gradle, Maven, and SBT, and we have all of these examples in Java as well, if you're interested in that. I will make a strong statement right here and on the record. Do not use Java if you have a choice. It'll be much easier to work with Scala, by far. Groovy? To use Groovy and Spark? I don't think anyone's done a lot of that recently. It works in the Scala REPL. So Spark actually comes with its own REPL. So let's say I wanted to play around with Spark Cassandra Connector in the Spark REPL. Actually, I don't want to delete any of that. That was silly. Basically, all we would change is we would delete all this stuff. I'll do a local example just because that'll make it really easy. We're going to keep this packages line. We're going to keep our connection to Cassandra line. And we're going to just change Spark submit to Spark shell. And that's going to just drop us automatically into a Spark shell where the Spark Cassandra connector is already on the class path of all of our machines. So the only things that you have to do at that point are do the import for all of the Datastax stuff. And once you've done that, it will automatically attach the Cassandra table method and the save to Cassandra table method. And I can do ks, kv, do a quick action like that, and there you go. Pulled all the data in a fun REPL-y way. One of the interesting things to know about Spark, and this is just another quick little detail, say I run this without the collect. Oh, it returned instantly. Does that mean that my code is really super fast? Is something cached? The secret is that Spark is a very lazily evaluated language. When I do this, I can do that. I can map my thing to, I don't know, length. I don't know if that's a member of that. OK, it is. So I can keep chaining operations onto this. But until I actually call an action, so an action is something like save to Cassandra. OK, thanks, autocomplete. Something like save to Cassandra or something like count, nothing actually happens. So that's something really important to know if you're trying to benchmark various things in Spark. Nothing will actually get done until you perform an action. So let me quickly reload that. Fun. There we are. And let's say we just want to do a count of this, which obviously is pointless. But you'll see that this count is what actually caused work to be done, not actually typing the line before then. Yeah, in the back?
In essence, there are multiple terminal operators in Spark.
There are various terminal operators that all end a single chain of operations, though. So the question is, where are there multiple terminal operators? And yes, there are. Common ones are collect, take, save as file, save as something. In the new API, which is the data frame dataset API, pretty much all of the sources are something called session.read, and all of the syncs are session.write. Yeah. OK, one more question?
If I started working on this with Python for the last month, you recommend switching over to Scala?
I said don't use Java. But so the question is, should you use Python? Python is really great as long as you stay within the data frames API. So this is something I didn't talk too much about so far. But basically, the way that Python works, and just for your information, the way you would start up the Python shell is very similar to this. You would just switch out Spark shell for bin PySpark. And I just basically did the exact same thing. But the way that Python works inside of Spark is that you write your code. You might write a Python lambda. You write that lambda as Python code. It gets shipped over to a JVM, which takes it and says, I don't know how to do anything with this. So it actually starts its own Python interpreter that it then serializes the code back to Python. So now Python's got its own lambda, and it can run stuff. But your data just got read in a JVM, so it's actually JVM objects. So now all of those have to get converted as well. So you serialize all those to Python objects so your Python code can work on them. But then you got to give them back to Spark, because let's say you have to do a shuffle. All that machinery is in Java. Well, you got to serialize it back into a JVM object. If you're using data frames, none of that applies. If you're using data frames, you basically are constricted to a bunch of operations that can all be handled within the JVM without having to basically go out to Python. There's a bunch of efforts going on right now to try to make better Python lambda serialization. But at the moment, just use only data frames. Yep. And I should wrap up. Thanks a lot, everybody. Oh, yeah.